Thanks a lot for the invitation. I would have loved to be there, but my daughter is graduating this week, so I had to stay in Stockholm. My name is Jesper Sollerman. I'm professor in astronomy at Stockholm University. I used to be the Swedish representative in NOTSA, and now I am the Stockholm representative in the new NOT board. I'm working on supernova and transients and things that explode out there in the universe. And I'm going to kick off this supernova session with a very personal, even nostalgic view about the relation between NOT and the Stockholm supernova group. It will go back to the 1990s and a little bit into the future. I will basically try to say how it used to be, which maybe wasn't fantastic, how I think it's now, which is great, and hopefully even better into the future. So when I prepared this talk, I went back and looked at my old observing logs from when I started observing with the Nordic Optical Telescope. These were the days, you know, when you had to do a lot of things on your own. I usually carried around a screwdriver to make sure you could fix the filter wheels. You had to fill the nitrogen yourself during the night in the dewars. And it was a great learning experience, although it maybe didn't always work out fantastically well. I remember coming down to the telescope once wanting to use the LDS spectrograph. And when I came up to the mountain, I was told, no, this is decommissioned. We don't have that spectrograph anymore. Let's try to do something else. This is my first spectra that I published from NOT data, upper corner here. And it's still the worst spectrum I've ever published. So it's only getting better. I was the only one in Stockholm doing observations of supernova. There were two more people in Stockholm when I started there mid-90s. They were both doing modeling. And when I came to La Palma for the first time, I really fell in love in the telescope. And I decided, yes, this is what I want to do. I want to do observations. And that was great. But I had to learn everything on my own, which was very painful and not very efficient either. But I realized that I actually sort of learned a lot when I came to ESO as a fellow, because learning a hard way is sometimes learning it the best way. So when I came back to Stockholm, I wanted to have more people have that opportunity. So I arranged a number of summer schools where people could come down to the observatory and actually use a screwdriver and play around with the NOT and with the Swedish Solar Telescope. And when I now look back at the image here, I see that there is a lot of the students from that time that are now sort of permanent all around in the Nordic countries, like on Iceland and Stockholm and Gothenburg and Vilnius and Turku. And even the teachers were pretty young at the time, but they are now sort of running the NTE or building the NTE or sitting in chairing the Royal Academy of Astronomy and things like that. I think this was great for students and for people and everybody engaged in the NOT. Not only for them, but also for NOT, that people actually got a good view of the NOT early on. And you will hear more in this conference about the pedagogical, the learning aspect of using the Nordic Optical Telescope. But I will talk mostly about supernova science and why the NOT is such a good telescope for that. It's because it's a very flexible and simple telescope to use these days. It's accessible and we can use it in a very complementary way with smaller and bigger telescopes. So for me, I normally use this telescope. This is the P60 telescope on Palomar, which I use every night to take spectra of maybe a dozen of supernova. I think the NOT is too good and great to use for just classifications. We can do classifications with smaller things. But when we realize that something is interesting that we recently classified, then it's time for the NOT telescope to actually come in and say whether this is important enough to follow up. And then when we find that it is, we can kick it on the supernova to bigger telescopes on Earth or in space. And this sort of complementarity is what is needed in transient astronomy. And that's why NOT is also so useful. I mean, if we had all the nights available on Keck, we could use that, but typically we are very constrained for big telescope time, and we can follow the evolution with the Nordic Optical Telescope. When I look back at my own PhD project that I showed you in the previous slide, That wasn't very clever, actually. I could go down to the knot 2 or 3 or 4 times a year, but we couldn't really follow supernova on a supernova timescale. So every time there was a new supernova that we randomly got a spectrum on. And today we do that much better, as I will come to in a minute. So first of all, you have to find the supernova if you want to do supernova science. And that has also changed quite a lot over the last 25 years that I'm covering here. So when I started in supernova astronomy, there were actually amateurs like this guy over here that found most of the supernova. He found 33 from his backyard in Australia. The record holder up until like 10 years ago was Fritz Zwicky, who found 100 plus supernova over 50 years. But most were found by amateurs because the professionals didn't really have any surveys to do this. This started with the HISED supernova team and similar teams doing supernova cosmology in the late 1990s. Basically, you could start up a campaign, like before full moon came on, you could do a search for a supernova, and maybe after full moon in the next lunation, you could try to get a spectrum to see what kind of supernova it was. The ESSENCE project that I also took part in worked in a similar way of finding and then classifying things. And SDSS, which came later, was the first that started doing things with more of a systematic cadence, using one single telescope every night to not only find, but also follow the transients, which is what we now do with the IPTF, the Palomar Transient Factory, and the current Zwicky Transient Facility that I'm working on now. When we do this in a more systematic way, and ZTF is also trying to classify the supernova in a more systematic way, basically doing all of them, then we don't only have to do supernova cosmology anymore, but we can start answering questions about the supernova themselves. What are the progenitors? Which kinds of stars are exploding? How does it actually work? And that's the aspect that I'm mostly interested in these days. The next generation is, of course, the Vera Rubin and LSST that will just boom what supernova science is in maybe 5 or 10 years from now. So during this epoch of time that I'm talking about, of course, we have published a large number of papers. I don't know, maybe 100 of papers. I will not bore you with citation statistics and that sort of stuff. But these are just papers that were actually led from people in Stockholm and then included also not data. And it's just a selection and they didn't fit on one screen. Which ones were most important? I'm sure that depends on who you actually ask. If you ask Claes Fransson, for example, he would probably say it must be this supernova, supernova 2010 JL, that we managed to follow with the Nordic optical telescopes for over 1,000 days. We got a fantastic sequence and complementary data from the Hubble Space Telescope in the ultraviolet. So putting all of these spectra and time evolution together, Claes could write a very long 100-page paper that sort of explains circumstellar matter interaction in a supernova in a very nice way. On the other hand, if you ask Ariel Gubar, which was the most interesting supernova we ever observed with the knot, he would probably pick this one with the funny name IPTF 16GEU. We got a spectrum of the knot early, figured out it was a type 1a supernova, but it was a bit too bright. And with the Hubble Space Telescope, we could see that it was actually lensed gravitationally. And here you can see the 4 images of that nice supernova. If you ask instead Matthias Ergon, he would probably say supernova 2011 DH. This is the front cover of his PhD thesis. This is a very nice image from the knot. This is M51, and this is the area where the supernova exploded. Here is a blow up of 2 pictures, and none of them actually contained the supernova. But the first one was taken before the supernova exploded, and it contains a star. And the next one is long after the supernova has faded and the star is gone. So we actually see the progenitor star here in this knot image. This is stuff you can do sometimes with the HST, but not so often with ground-based telescopes like the knot. Matthias is only one of several PhD theses that we have gotten here in Stockholm, based in a large part on data from the Nordic Optical Telescope. Some of the papers that we have written over the years have reached into sort of high-pitched journals like Nature and Science, and I will not go into the details, but there is one theme that I think is particularly interesting, and that's this new theme of flash spectroscopy supernova. So if we get to the supernova early enough, we can find some features that we call flash features of high ionization lines that provides information about what the star did in the last maybe 50 years before it exploded. And these are not accessible if we don't get the data very, very early. So here is a light curve. Here's a typical evolution of a supernova. So with the Zwicky transient facility, we observe the same patch of the sky basically every night. Here we didn't see it. Here we didn't see it. Here we see it. So that means we actually know that it exploded in this short interval here. And we catch it on the rise, and every tick mark here is when we got the spectrum of it. And the inset here actually shows hours from explosion. And I already think this is quite amazing. Remember, I said that when we started with the HiSED supernova team, we tried to find the supernova one lunation. Maybe we found it here. Then we had no information of what it was doing earlier. We couldn't say how old it was. We never got the rise. And then maybe a spectrum over here, when it was much too late to see any of these flash ionization features. So this is a nice illustration of how much better we can do today with these systematic surveys of supernova, and what we can actually learn from getting data that early on. And you can see that we got early Keck data, but then it was not that found the feature here as well, and then not that saw that the feature had disappeared, which includes information about this shell around the supernova. This, I hope, is my most important slide, or maybe impressive slide. Instead of showing the papers that I showed you 2 slides ago, these are the faces of all the people that actually wrote the papers. So everyone here worked at Stockholm, and they wrote a paper as lead authors, including data from the Nordic Optical Telescope. That's quite a bunch of people, and it's quite a legacy for what the NOT has actually done. So people here worked weeks, months, and as you know, sometimes even years on NOT data to get these papers published. And there are more people that has been working in the supernova group in Stockholm that are now in Copenhagen and Turku and Aarhus. So the transient community has really exploded. Remember, I said there was no one when I started doing supernova observations in Stockholm, and now we have this pretty large group. So I think that's a nice legacy. And that's because we have made the NOT a good telescope for doing transient science. So now there are a number of groups, and you will hear presentations from them after my presentation. And everybody is doing great and interesting stuff with the NOT. I will present a little bit the Zwicky transient facility that I'm working on. We use this telescope over here, the P48 telescope, every night to look at basically all of the northern sky, because we have a huge camera. It's sitting over here. So when I started observing with the NOT, I used the Stockholm CCD. It was 512 pixels. It was this small, if you can see me. Today we have a, can you see this? Huge CCD camera, 47 square degrees, 600 megapixels, that scan the sky every night. And then my job is to find the supernova and send them over to this telescope, which is the P60, where we have a robotic spectral energy distribution spectrograph, and we take spectra and we classify them. So I think this machinery gives us a huge number of supernova, and it sort of works. I will start this movie. Here is the dates, the number of supernova that we have found, and you can see we are populating the sky all the time. And the completeness is how many of the supernova brighter than 18.5 did we actually classify. And our completeness now is something like 95%. I will let it run here while I show you this. This is the Bright Transient Survey Explorer. It's a web page that is publicly available. You can go in there and you choose your favorite supernova. I chose the stripped envelope supernova, the ones without any hydrogen. These are my favorites. And I click, and it tells me that we have already found 300 of those. Upper limits before we find it on the rise. We get it in 3 different filters. So whatever science that you can sort of dream up of that you could do with samples of supernova like this, you can just go in and get this data yourself. And the clock is ticking here until today. I don't think it's completely updated to 2022, but now we have 6,000 supernova that we have classified, more or less. And the many, many more that we haven't classified. I think I have probably discovered 6,000 supernova myself. So it's a long time ago since you could have a record with only finding 33 or 100 supernova. When we do this, we can do all kinds of population statistics, of course. This is one of our favorite diagrams where we show the luminosity, how bright the thing is versus how the duration of the event, with a long time event or a very fast duration event. And you can put in any kinds of supernova or other kind of transient in this. And with IPTF and ZTF, we have discovered a huge number of new objects, new classes of objects, but you can also get a feeling for the known ones, sort of what is the range of type 1 BCs, how bright can they be, what is the typical one. And you can, in a plot like this, you can sort of pinpoint and say, hey, this point is somewhere else, what is that? And someone can go and write the paper of that particular long-lived, low luminosity type 2 supernova. So it's sort of a gold mine for doing all kinds of things when you get a complete sample where you know what you're looking at. So I'm going to end with what's next. Next is, of course, the Vera Rubin LSST survey, which is going to be much bigger telescope than the ZTF, a much better telescope than the ZTF, and in a much, much better site. So it will find 10 or maybe 100 times more transients than the ZTF. We are up for a tsunami, a real data tsunami that I'm hoping that we are sort of prepared for. But this will go like 4 or 5 magnitudes deeper than ZTF, and we will find hundreds of thousands of supernova. So what can we do? Can we classify all of these? Can we even look at all of them? I'm not sure. But I'm hoping that NOT and the NTE will play a part of this. So we in Stockholm, we are currently part of the NOT. We will be that until beginning of 2024. Thereafter, I'm hoping that we can participate in a project where we can classify LSST supernova using the NOT and the NTE. In fact, we have already funding for this project, and we have suggested this for LSST as in-kind for what we are doing in Stockholm. So I hope this will be interesting for the supernova community, 300 hours of spectroscopy classification of LSST targets over the next 3 years. And I'm thinking this is also probably good for a NOT telescope that needs some sort of income when Sweden and Stockholm is not participating anymore. So I am sure that we have many, many more interesting supernova to find, and I'm very happy that I started observing with the NOT and got in love with these telescopes, so I didn't have to do supernova modeling and could do observations instead. Thank you very much. If you have comments and questions, I can try to answer them now, or you can also send them to me via email. So, thank you.